Okay, going to do a quick little talk through about significant digits or significant figures, however you want to call them. First off, I'm going to say they're not the most exciting of things. For some of you, it's going to bug you and give you a headache. But as we move forward and get into labs, they become a little bit more important, and it's something we should go over at some point. So I'm going to talk you through this PowerPoint. If you don't want to hear me talk, you can just stop the video and scroll through the PowerPoint on your own. But I'm going to talk you through some of the basics, and then there'll be some questions for you to try at the end. First, as I said, it's kind of more important when you're doing labs. But really, there's two kinds of numbers. The one we would call an exact amount of numbers, like if I asked how many people are in the classroom, we should be able to count and get an exact number for that. Or if I said how much money is in your bank account, we should get an exact amount for that. But then there's other quantities that, even though we might try our best, they're always going to be a little bit approximate. Maybe we can invent a better tool to get it closer to perfect, but anything that you measure is always going to have a little bit of uncertainty or be a little bit approximated. So the words I will sometimes use are uncertainty, like how close we are, the farther away we are from actually knowing it, we would say that's a more uncertain measurement. Or if there's a lot of error, that means we didn't do a very good job at measuring it. In science, we want to have our numbers to be as certain as possible or as small of an error as possible. But how much uncertainty and how much error, we'll talk about that another day. That is going to come down to what's doing the actual measurement. Are you using like a beat up old meter stick, or are you using some sort of laser range finder that's maybe more accurate? Anyway, on to significant figures. A significant figure, really what it means is based on the tool that did the measuring, that significant figure is accurate. That figure sort of counts and is important. If I gave you a small job to do and you measured that a piece of paper was 27.1 centimeters across, that would be a great answer. 27.10, 27.100, to a mathematician, those are exactly the same. But to a science person, this second one that has the extra zero, that implies that you did a better job measuring it. You were more accurate. You could get it down to the 1,000th of a centimeter, and you're confident in that number, and it just happened to be a zero, as opposed to the 27.10. You measured it confidently. You could get to two decimal places or the hundredths, and it just happened to be a zero. So from a science person, if you showed a science person those two numbers, the science person might say, wow, look at this number. Whatever they used to measure this one, they used a really good tool. It got an extra decimal of accuracy. What that means for what we're going to talk about today is that this number over here has more significant figures than this number here. This number on the right will work through the rules, but this actually has 5 significant figures, where this number on the left only has 4 significant figures. But we'll talk through the rules. When you're using significant figures, there's a few rules, so we'll kind of talk through this and then get you to practice some. Basically, the first rule, any number that's not a zero is significant. So a number like 125, that's got 3 significant figures. The 1, the 2, the 5, they all count. A single digit number has got 1 significant figure. A 2-digit number has got 2 significant figures. A 4-digit number has 4 significant figures. If it's a non-zero, then when you're counting it, it's a significant figure. Gets a little bit dicey when there's zeros. So first rule to deal with the zeros. I'm never going to call it the sandwich rule, but if we've got a zero in between non-zero numbers, so like this, 1009, 1009, all 4 of those digits are significant. Those middle zeros just happen to be zero. Maybe if it was a slightly different thing, it might be like 1129. Just the flukiness of whatever did this measurement, it happened to have zeros in it, but those zeros in between two non-zeros, they count as a significant figure. So this first one here, 1009, 4 significant figures. 502, that middle zero counts, so 3 significant figures. This number, 74,056, the zero counts, so we've got 5 significant figures. Even if there's a decimal place, 60.8, that zero counts as well, so that's 3 significant figures. So zeros in the middle count. They just happen to be 0, so they count as a significant figure. If we've got a number smaller than 1, so like 0 point something, then the first zeros don't count. So for example, 0.95. This first 0, it doesn't count. So that's a 2-digit number. This number, 0.4003. From our last rule, these zeros count, but from this rule, the first 0 doesn't count. So that's a 4-digit number, the 4, the 0, the 0, the 3. 0.2, that's a 1-digit number. The leading 0 doesn't count. This is where it gets weird. 0.008, these first 2 zeros don't count. They're just placeholders to get the 8 in the right spot, so that is a 1-digit number. So leading zeros gets a little bit messy. If we're smaller than 1, the leading zeros do not count. Second 0 rule, well, another 0 rule, third 0 rule is if there are trailing zeros, they do count. So this one doesn't have any trailing zeros, the sandwich rule idea. All those zeros in the middle count, so we've got 1, 2, 3, 4, 5 significant figures. This one, oh, I think I might have said it backwards. Trailing zeros do count. Sorry, trailing zeros are significant. So a number like this, 0.9300, our science person took the time to write these extra zeros. They just happen to be zeros. They do count. They're significant. The person took the time to write them to emphasize that they count. If they didn't count, the person would have wrote just 0.93. But because they count and happen to be 0, they got written down. So 0.9300 is a 4-digit number. All 4 of those count. Similarly, 5.00, all 3 of those count. So that's a 3-digit number. Where it gets a little bit weird, oops, 0.0070. The leading zeros don't count. That's that last row. They just happen to be 0, but this trailing 0 counts. So that's a 2-digit number. I know there's a lot of rows, but once you get the hang of them, it's not as terrible as it sounds. All right. We talked about numbers that were smaller than 1. If we have numbers that are bigger than 1, the trailing zeros are not significant. So a number like 20, only the 2 counts. That's a 1 significant number. 300, only the 3 counts. That's 1 significant digit. 150, 2 significant figures. 20,000, only the 2 counts. I'll teach you a trick for when we need those zeros to count if they are important. We would just switch to scientific notation. But for these numbers, if you just have raw numbers like that, 20 is a 1-digit number, 150 is a 2-digit number. Those trailing zeros, they don't count. So we don't worry about the trailing zeros. They just happen to be there kind of as placeholders. All right, that actually is all the rules of how to count the digits. Now we've got 2 more rules about how we work with the digits. There's going to be rules for adding and subtracting and multiplying and dividing. For adding and subtracting, we literally look at the number of decimal places. If we're adding numbers in a lab or something when we're actually paying attention and significant figures are important, if we're adding numbers, then we look at 2 numbers, which whenever has the least amount of decimal places, we're going to match that. So for example, let's say we take 4.8 milliliters and we have to subtract this crazy number, 3.965 milliliters. The mathematical answer is this, 0.835. But when we apply our digits rules, this one only has 1 decimal place, where this one has 3. So the rule for addition and subtraction is you match the fewest amounts of decimals. So although the calculator said 0.835, we need to round that to 1 decimal place. So 0.835 rounded to 1 decimal place becomes 0.8. The notation is basically an equal sign with a little circle on top, or I've also seen, instead of an equal sign, the top line gets squiggled. I'll take either one of those. If you're typing it, whatever's easier to find. But our digit rules, when adding or subtracting, we have to round to the fewest number of decimal places. This one's already typed up so you can kind of read along. Let's say we needed to add 3 numbers, 2.50, 1.4, and 3.198. When you do the math on that, the calculator is going to spit out this number. If we're doing a good job with significant figures, then we have to round that off to match our rules. Our rule for adding is the fewest number of decimals. 1.4 only had one decimal place, so we have to take this 6.098 number and round it off to one decimal place. So rounding it off, it's closer to 6.1. So squiggly line 6.1, or the equal sign with the dot 6.1. On an everyday basis, if I'm just making up a question on the whiteboard, we're not going to worry about significant figures. But as we get into lab work, that's when I'll push you to do significant figures. Don't worry about it for questions we're doing off worksheets and whiteboards, but we'll worry about when we're doing labs. Okay, there's one more rule. I'll talk you through this rule, and then you can practice them on your own. Same basic idea, but for multiplying and dividing, instead of looking at the decimal places, look at the total number of significant digits. And whichever one has fewer, that's what we're going to round off to. So for example, let's say we take 278 grams and we need to multiply by 11.70 grams. When you put that into your calculator is going to spit out this crazy number, 23.7601. A little typo on here. I don't know why you'd ever multiply grams by grams, but it should be grams squared. So G squared, or maybe G stands for something different, but G squared. Now, significant figures rules for multiplying and dividing are we look at the number of figures. This first number is a 3 significant figure number, and this one is a 4 significant figure. The trailing 0 counts. If we multiply a 3 by a 4, then we have to round our final answer off to 3. So 23.760, rounding it off to 3 decimal places, it's closest to 23.8. Again, you could do this squiggly line, 23.8, and the units would be G squared. Just like adding and subtracting, we're not going to worry about this when we do worksheet problems or questions on the whiteboard, but we'll pay more attention to it when we're doing labs. Okay, a few multiplication examples. If we take 6.38 and multiply by 2.0, again, I'm not sure why we'd multiply milliliters by milliliters, and another little typo, this should be milliliters squared. More important for what we're talking about, the number of digits. When we put it in your calculator, you're going to get 12.76, which is a 4-digit number. But following our rules, we have to round it back to 2 digits to match that. So 1276, close to a 2-digit number, becomes 13. Next example, 100.0, how many digits is that? Divided by 2.30, how many digits is that? Again, I borrowed this and I didn't proofread it well enough. The grams would cancel. If we take 100 grams and divide by 2.3 grams, calculator is going to say 43.47826, but we need to now consider the number of digits. This is a 4-digit number. This is a 3-digit number. So rounding that back to 3 digits becomes 43.5. The last one, units are mixed up again. 710 divided by 3.0. This is a 2-digit number, and this is a 2-digit number, so we need to round our answer off to 2 digits. So it gets a little bit wonky, but 236, making it a 2-digit number, would be 240, because remember that trailing 0 doesn't count. This last example kind of rattles people sometimes, so another way to deal with significant digits would be to put it in scientific notation. 2.4 times 10 to the 2, this is a 2-digit number. So 240, we could also write as 2.4 times 10 to the 2. Then it becomes really clear that the digits are significant. In our 43.51, we could write 43.5 as 4.35. That's a 3-digit number times 10 to the 1. That's where I'm going to pause the video, but when you go on, I'll post the worksheet. Since you can't click it in the video, the worksheet will be posted. When you're doing the examples, the answers, again, I borrowed this, actually was given this with permission. Some of your answers are going to be in scientific notation, so maybe you might have to do a little Googling or talk to someone close by, see if you can remember how scientific notation works out. The bottom line for all this is it's going to bug some of you. It's just following rules. And really the big bottom line is when we're doing questions off worksheets, when we're doing questions on the whiteboard, we're not going to worry about significant figures. But as we get into labs, and I'll point it out where I want you to really work on it, but as we get into labs, we'll definitely start paying more attention to significant figures. So read through the examples again if you want, and then you can take a look at the worksheet now.